Then, Mr. Klaus, you can start it again. Okay. So let's come to the calculation of the pressure drop inside the pipe system. And it's exercise 5.1. Pressure drop in a pipe system. And that's an important topic. This is a really important exercise. You might also need it for the exam. And you have, for example, a vessel here. Yeah. It looks like this. It's your first vessel. And you can have a vessel that is a bit lower, or it can be higher. Anyhow, vessel here. And now at first what we need the pipe, and the pipe goes for, okay, the pipe goes from this to this direction, and we have the height of, yeah, the height difference is here from Z equals 1 meter, and we have here height of Z is H. Okay, and now we want to calculate the velocity. Yeah, the velocity C1 at which the water flows here into the vessel. One. So this is basin 1. This is 2. And we have the velocity here C1. Okay. And first step we have to do, we have to formulate our Bernoulli's law. Yeah, and we have to take into account also the losses. But before we start with the calculation of the losses, we will just say, okay, the losses might be 0, we have no losses, and we make the first calculation without any losses. Okay, so we formulate it, and we formulate it P2 equals no, it's more plus let's call it R1. Okay, But we now need an additional law. Yeah, we now need an additional law for the pressure drop, and the law was formulated in the slides. And I will open it to you. Okay. So plus one, two. And this part now is more or less unknown. So at our first iteration step, we will set it to 0. But of course, it will not be 0. Yeah, it will be higher than 0. So in the first iteration, we set this to 0. Okay. So let's do the first calculation. Okay, we need P2 and P1 is the same. Yeah, let's say P2 equals 1 bar, P1 equals 1 bar. Then we get and O1 is let's say 4 meters plus.
I have a question to that. Why is P2 equal P1?
Yeah, P2 and P1 is just the pressure of the air outside. This is the pressure here over the basin. Yeah, the pressure here and the pressure here. Yeah, and it's the atmospheric pressure.
Okay.
Pressure. If there is, look, maybe if this is closed, and you have a higher pressure, yeah, maybe 2 bar, you have to take this into account. But if it is open here and both are open, they will have the same pressure because the pressure of the air will not change so much. Yeah. So, or if you have a really big height difference, the pressure can change. The pressure of the air can change. But here in this example, both basins are open and you don't have a big difference in the pressure. So you can say both are atmospheric pressure of the air. And you won't have a big problem. Okay? And then you can say you can neglect them. Okay. But important is now the height, the difference of the height. And we must take into account h as the first height, and we must add plus z2. So we must need okay. Do you understand this formulation here? Are there any questions? Of course.
Shouldn't it be C1?
Yes,
squared?
of course. C1, of course. But the height is clear, yeah? It is the height of the water column here. This is clear, huh? Okay. And now let's do a second estimation. Okay, let's go on. And okay. And let's say the velocities are the same. Or we do it in a different way. First we say the velocity is really small. There's okay, it has the same difference. Okay. So okay, first we say we estimate. Let's say the difference here is, let's say the velocity here is 0, c2. And then we can write c1 squared equals, and subtract this. Okay, divided by 1 equals okay. And there we have okay, my calculator. Okay, this is now our first rough estimation of the velocity, but now we need an additional pressure drop for the pipe. Yeah, it is written here. We have to recalculate it, and to do the calculation of the pressure drop, we first need to know if this is a turbulent flow or a laminar flow. So write it down. Don't want to miss it. So C1 is 8.85 meters per second. And now I want to know, is the flow laminar? I take this first estimation of C1 to estimate if we have laminar or turbulent flow. So I have to calculate the Reynolds number. And the Reynolds number is really important for you. You calculate it by D. Okay. And then you can calculate density. Cubic. Centimeter by okay. And now I calculate it, and be careful here with the centimeters. Okay, and I have a really high Reynolds number. It is about okay. So it is a really high value of the Reynolds number, but it depends on the it depends on the really small viscosity. And now I have to look into the Moody diagram. And maybe can you tell me, is this laminar or turbulent? Can you tell me now, is this flow turbulent or laminar? Can you give me short feedback? Is this turbulent or laminar flow? Hi. Okay, it's really high number now. This turbulent. And now I have to, yeah, Mrs. Claire, perfect. It's turbulent. And now we will need the diagram in the slides. I want to share the diagram in the slides now. It is the Moody diagram, and we have to look up if this behavior is now laminar or turbulent. Okay, maybe you can see the slides. Yeah, this is a formula for the pressure drop. We will need it later. And we have to change to the Moody diagram. That's the Moody diagram. And the Reynolds number was about here, this area, highly turbulent. And so we have to take, let's say, a lambda value. Let's take a lambda value of 0.001. Might be a good value. No, it's a small value. Let's take 0.001. And share it again. Okay. Okay, give me a short thumb up if you see the whiteboard again. Give me a short thumb up. Perfect. We take a lambda value of 0.001. And now we can calculate our pressure drop for this value of 0.001. That's okay. And we need the formula here. O times 2 equals lambda d plus sum of zeta times okay, that's a formulation of the pressure drop. Yeah, now we want to look into our picture and we want to formulate the pressure drop. Okay. Look at the pipe. We have here an armature, an elbow. We have here an elbow. We have here this other armature. So we have L1. here this. So, so okay. So we sum up. We first write down the pressure drop. So equals okay. Good. And to define this term, and the sum of L is L1 plus L2 plus L3 plus L4, and it is 3.4 meters plus 3.6 meters plus 1.2 meter plus 1 meter. And this is meters. Okay, and now we must, so this is 0.01 meters divided by 0.03 meters. And now we must calculate the sum of the zeta values, and we have zeta here, 0.4, and we have no units at the zetas. We have a five. We have a zeta for this value. And we have a zeta here. Okay, now we sum up all the zetas. Yeah, and this two zeta k, they are the same. Yeah, this and this are the same values because they are both the same elbows. Yeah, they have the same zetas. And here for this armature, we have a zeta of 0.18. So I sum it up. And it will be 0.4 is 1.28. And we don't have any unit here. So I can add this to 8. Okay. So times 9, 8. Not so good. I messed it a bit up. So 2 times, and the velocity was, I think, 8.85 meters per second. Okay, I wipe the board a bit. Okay. Okay. Much better. So I have 0.01 and 3 plus 4, 6, 2, and this should be Pascal. Yeah, this is a pressure drop in Pascal, and it's not so much. Yeah. Pressure drop in Pascal. Okay, so now we can take this pressure drop and make and repeat the steps and add it to our Bernoulli equation. Okay. Okay, is this now, and maybe that's a step you can do by your own, and you can repeat the whole calculation, but now additionally with the pressure drop. Yeah, I can write it down for you. Now we make the next iteration step. So second, oh yeah, now I have a call from another person. I have to answer it later. So guys, can you see the screen? Maybe give me short feedback, because I do not see the my own screen. Can you see it? Okay. Can you now see the screen? Mr. Seiler, can you see the screen? And now? Okay. 1 second. I just got another call from someone. I just must answer. Okay. So okay. So hello guys, can you see now? Can you now see the whiteboard? Can you now see, Mrs. Claire? Can you now see the screen?
I can still not see it.
Okay. And now, can you now see it?
No.
Okay. It's not really cool.